Hi everybody, Dario Fresu here from fresuelectronics.com, and today we're going to talk about the power delivery network. So how to build a power delivery network in terms of EMI and signal integrity, specifically for the digital circuits that we are designing. Alright, so before we start talking about how to build a power delivery network, we need to talk about what are the requirements of the power delivery network. And this is important, like in any other system, we need first to specify the requirements and then we need to start building it. So the requirements that we have is first of all to provide a constant uninterrupted DC voltage source to the load. So we want the system to maintain constant supply during the operation. This is important because of course you don't want to have your processor or your microcontroller being interrupted during the operation. So we need to provide a constant power supply, so a constant voltage source to the load, which in our case is most of the times the ICs. So then the second requirement is to avoid any AC noise within the power delivery network. This is important because otherwise this noise can spread throughout the whole PDN, and then this one will reach either ICs, so we will have some signal integrity issues, or it can also spread around and cause some EMI issues by coupling through the cable or radiating. So then the next requirements that we have is that we want to have a 0 ohm AC impedance between the power source and the return reference plane. So one of the ways that we're going to achieve this goal is by choosing the right decoupling strategy. And what do we mean by that? We need to choose also the coupling capacitors that serve several functions. So one of the functions of the coupling capacitors is actually to reduce the dependency from one integrated circuit to the other. Why this is important? Because imagine that you have one processor which is requiring some very high transient currents from the power delivery network, and then you have another processor which is requiring at the same time as well some transient current. So what happens is this in this case is then if the power delivery network cannot supply this current, then we will have some voltage dips, and then if we have some voltage dips, this means that some operation from the processor, they are going to be interrupted, or the processor can be switched on and off. So we don't want to have this kind of situation. So we want to separate the dependency from one IC to the other one. So one way that we're going to achieve these goals is by choosing the right decoupling capacitor strategy. And we have to think, first of all, what are the functions of the decoupling capacitors? So we have two main functions, which is one, to reduce the dependency of one integrated circuit on another. And then the second is to reduce the impedance between the power and the return reference plane. So we know that digital circuits are composed of logic gates. These logic gates must switch at a fast rate to provide the required digital signals. So for these fast switching events to occur, a transient current in the power delivery network is then required. So this means that each time we have this fast switching of the logic gate, the IC will require some transient current, which is going to basically power this switch of the logic gates. Then this transient current has to propagate through the power delivery network, which means it will go through also its impedance. So the farther you have the power delivery network, the more impedance you would have in between. So what we want to do is to actually reduce this impedance so that in this way we also reduce, by reducing impedance, we reduce the voltage drop, which is created by the current flowing through this impedance. So we have to think not in terms then of resistance, because if we just think about the resistance of the copper, then the problem will be solved much easily. But we have to think also about the inductance and the capacitance that we have in between. So the most important for us though is the inductance between the traces. Why this is important? This is important because first of all we have some transient currents. So this means that we will have a certain frequency connected to this switching. And this is important because we have the inductance which is dependent on the frequency. So also this voltage drop is important because not only is important for one IC, but it's also important because if we have a voltage drop in the power delivery network, then this voltage drop would be perceived also from all the other ICs, and we don't want that. So the other problem that we have related to this transient current flowing through the loop created by the power source to the load and back to the source through the return reference plane, is that these loops can become very effective antennas. So to decrease the voltage noise generated by this transient current, we have two main choices. One is to reduce the transient of the required current, but this means that then we will have an impact in the timing and also on the efficiency of the PDN, of the system. And the other one is to reduce the impedance of the PDN, particularly the inductance of the PDN. So this is clear because as designers, we can have the most impact by reducing the inductance of the PDN. So we cannot really change the requirement of the transient current. So the way that we're going to achieve this power delivery network optimal performance is by using return reference planes, but also by engineering the power path with the lowest possible inductance and resistance. So one of the most efficient ways that we have is to reduce these current loops, so reducing the transient current loops from the power source to the load. And this means that we have to bring the power source basically closer to the load. And one of the ways that we're going to achieve that is by using the coupling capacitor. So by using the decoupling capacitor, we are basically bringing a source of energy as close as possible to the IC. And this means that then also the inductance between the decoupling capacitors and the IC can be reduced because the decoupling capacitor can be placed very close to the IC, so the inductance of the traces can be reduced. Okay, so we mentioned that these transient current are generated by this logic gate during the switching time from going from the low state to the high state or vice versa, so from the high state to the low state. So this is important because this means that we cannot really have an impact on the timing of the switching because otherwise we are going to reduce the performance of these logic gates. What we actually want to do is to create a perfect environment for the power delivery network so that we can bring this transient current when they are most needed. One of the things that we have to distinguish now is these sources of transient current, because we have two main sources of this transient current. So the main sources of these switching currents that we have within the logic gates are these shoot-through current, which happens when both of the FETs are switched on simultaneously, and then this transient load current, which is when the CMOS, basically the logic gate, is switched on and charges this load capacitance here. So the amount of each current will be determined by the type of integrated circuits and application that we have. So for example, for processors, FPGAs, and microcontrollers that have a large number of logic gate switching within, then this means that the shoot-through current will be more prominent. If we have instead some other IC where we have a large number of pins being used as input and output and connected also to external loads, then the transient load current will be more prominent. So if you really want to go a little deeper into this topic, you can just check the books from Archambault and also from Oz. So now the question really is how we are going to calculate these currents. So in order to find IL, we can use this capacitance here, multiplied by the VCC voltage there, divided by the time that it takes for the transient current, and then we can multiply this by the number of logic gates that we have inside the IC. And this will give us an estimate of this transient current that we have. So then to calculate the shoot-through current is a little bit more complex because usually we don't have this data available in the datasheet of the IC. So one way to estimate this shoot-through current is by using the equivalent power dissipation capacitance, which is usually reported instead in the datasheet. And we can really think about this capacitance as a capacitance per gate. Otherwise, some of the manufacturers will give us also the shoot-through current parameters by specifying it in ampere per megahertz. And so once we have that, we can use these parameters to calculate this shoot-through current. So the calculation then will be this shoot-through current given as ampere per megahertz. So we can just multiply it by the frequency and then we have the shoot-through current. The other method, instead, will be to calculate it from the power dissipation capacitance given in the datasheet. So we can multiply this power dissipation capacitance for the VCC and then divide it by the transient time of the shoot-through current, and we can multiply that by the number of logic gates that we have inside. So both methods then are pretty similar. So to calculate the transient load current, we are using the load capacitance, and instead to calculate the shoot-through current, we are using this power dissipation capacitance given in the datasheet. Still, we are going to divide it by the transient time of these currents, and this time is typically the rise time and the fall time of the logic gate, which is given in the datasheet anyway. So before we proceed, we actually have to start to demystify some of the concepts that we have about decoupling capacitors, because these are widespread within the PCB community. So we need to really take a look at those. One of the concepts that is quite widespread is that we can choose different values of capacitance to improve the power delivery network. And this is not necessarily true. And why this is not necessarily true, I've explained already in another video, that we have this phenomenon which is called the anti-resonant frequency, or also the crossing of the impedances of each capacitor. So we know that the capacitors has a certain impedance profile, which is basically capacitive up to a certain frequencies, which is the point which is called the resonance frequency, where then the capacitor starts to become inductive. So up to a certain frequencies, we have the behavior of the capacitor that we want, but then the parasitics effect will start to take place and the capacitor will become inductive. So if we have an overlap of these different type of capacitors, then what is going to happen is that we're going to have these cross impedance profiles, and they're going to create some high peak of impedance within the power delivery network. So we don't want to create these type of phenomena, because this can create serious troubles in terms of EMI, but also in terms of signal integrity. And so what we want to do is we don't want to choose different values of capacitance in here. So we don't want to choose one bigger capacitor and then another smaller capacitor. But what we want to do is to select a certain value of capacitance for the chosen package, so that then we can calculate how many of these capacitors we are going to need in order to build the impedance profile that we want. This will become very important because each time that we are placing a capacitor, we have to think not only that we are placing a capacitor, but that we are placing an LC network. And this is important because this means that we are going to have also some resonant frequencies, as we know from the LC circuits. And then we have to be careful about this type of phenomenon. So now, talking about the inductance, where this inductance is really coming from. This inductance is coming from, first of all, from the package itself. So from the package of the capacitor. So this will have quite importance when we are selecting which kind of package we're selecting, if it's going to be a through-hole component or if it's going to be an SMD component. So this will become important because the inductance is related to the package, but then also is related to the inductance of the traces that we have. So the way you're going to route the capacitors to the pin that they are feeding is very important as well, because the inductance is dependent on this trace which we're connected to. And then we are also having the inductance of the pins, which of course we don't have much control over it. So as a designer, we really have only two parts that we can control. One is the inductance of the package, which we can actually choose by selecting a different package. And the other one is the inductance of the traces, which we can control by designing different traces. So by designing different geometries of our traces. And this means that the layout itself then will become very important. So you see, this is already one of the connections that we have between the EMI performance and signal integrity performance and the layout itself. Okay, but so if we have this inductance, then we need to take into account what is going to be this resonant frequency for the capacitor that we are selecting. How this inductance of the package, the traces and the pins will have an impact on the resonant frequency of this part of the power delivery network. And we can actually calculate that. This is the regular formula that we have of the resonant frequency, which is actually 1 over 2 pi times the square root of L times C. So by knowing the C and by knowing the L, we can actually calculate what is going to be this resonant frequency. And so the frequency where the capacitor is going to be effective, and then it will start to become inductive. So this means that for high frequency, it's not really important which kind of value of the capacitance we're using, but it's far more important what are the inductances related to the package itself. Now, to give an example, if we are using a 0.1 microfarad capacitor, and if we calculate the inductance of the package plus the traces and the pins, then this usually amounts to 15 nanohenry. So if we take this data and we calculate the resonant frequency of the capacitor by using the inductance of the package plus the inductance of the traces plus the inductance of the lead of the IC, then the capacitor will be effective only up to a 4 megahertz frequencies. So up to 4 megahertz, we're going to have this nice capacitive filtering behavior, but frequencies higher than 4 megahertz, we are going to have inductive behavior. So the best way that we have to design this power delivery network is to actually select the package and the capacitance value, and then to multiply these so that we have an effect of a parallel capacitance. And also in this way, we're going to reduce the inductance. Think about this, that we are going to have these multiple capacitors with the same value. So the current is well distributed within these capacitors because it's going to be the same current for each capacitors. But then the capacitance is going to be multiplied by the number of the capacitors that we're using in parallel. And the inductance is going to be reduced because we're placing it in parallel. And this is exactly the effect that we want. And so if we want to achieve a low impedance, these will be the best strategies that we have. So now let's have a look how choosing the right strategy for the decoupling capacitors and also the placement of the decoupling capacitor is going to have an impact on radiated emissions. Really, the problem comes from the inductive loop that we create. So we know, for example, this is a power pin and this is the ground pin. So the loop that we're going to create is the loop that is going to be from the power pin and the capacitor, but also from the return path. It goes through the via there, connects it to the return reference plane, and then it goes back here. There will be another via, and it will go back to the ground pin. You have to think that if you place this decoupling capacitor far away, so if you take these decoupling capacitors here and you place them here, for instance, then the loop that we create from this pin is going to be much larger, and this loop will have some transient current flowing through it. So this means that if we have some transient current flowing through it, changing current means that we have also an induced magnetic field. And so these will become important because this magnetic field then can couple to other traces, can couple to other cables, and then once it is within the cables, then it can start propagating and radiate. Then the other problem that we have with the radiated emission is that once we have this transient current flowing through these loops, then we have also a certain impedance connected in the return reference plane. So when we're thinking about the current, we have to think about also where the current is flowing through. And in the return reference plane, the larger this loop become, the larger this voltage drop that we're going to have is going to be. And this means that this voltage drop then can couple also to other cables and to other traces. And then this voltage drop then will cause the radiations. But also the other problem that we have to mention is that if we place this one farther away, let's suppose that we are placing these capacitors here, we are placing them there, farther away, then we will have also this part of the connection, which is where we can couple also some noise from the other traces routed across these points. And then this noise can couple to the power delivery network. And once it couples to the power delivery network, then it can also reach through the whole delivery network. It can reach also other ICs, and then the connection is then these ICs can also be connected to the cables, and then these cables will radiate at certain frequencies. Okay, so what is now the strategy that we have to really optimize this power delivery network? How we're going to calculate this target impedance, how we're going to select the impedance that we are allowed to have in our system. So to select the target impedance that we want to have in the power delivery network, what we can do is to actually check what is the voltage allowed by the IC that we're using. So what is the maximum voltage drop that we can have in our IC? And then by using this voltage, we can divide it by the transient current of the circuit that we calculated before. And this will give us the impedance. So the voltage drop that we are allowed to have in the IC divided by the total transient current that we calculated before from the two main sources. So from the shoot-through current and from the transient load current. So this simple formula then will give us the target impedance of the board. And then we can use this target impedance of the board to calculate also how many capacitors we need to have and what is it going to be the total capacitance that we need to have in order to guarantee this target impedance for low frequencies. I say for low frequencies because we saw before that really at high frequencies, the only way we're going to reduce this is by choosing multiple capacitors in parallel with each other so that we can reduce this inductive effect. We can see from these other capacitors here will rise at basically at 20 dB per decade. So this is 20 dB. And then you can see that from one point to the other one is basically increasing. The inductive part increases at a rate of 20 dB per decade. But why we don't care much about this increase of the impedance at high frequencies? Because we know that the signal itself, the spectrum of the signal itself, thanks to the Fourier transform, will decrease at a 40 dB per decade after a certain level of harmonics. And I'm going to show you that. So what do we mean that the spectrum of the signal is going to start to fall at a rate of minus 40 dB per decade? I'm going to show you here an article from In Compliance magazine where Bogdan Adamczyk explained this very well. And it shows you also the calculation that you have to go through. I want to keep this simple, so we're just going to have a look on what does this mean for us as designers. So it means that if we have a trapezoid-shaped pulse, so if we have these transient currents required from the IC during this switching of the logic gates, then we can calculate the Fourier spectrum of these signals, and we're going to obtain something like this, which is basically the bounds of the harmonic frequency that are going to be contained within this spectrum. But this tells us that the spectrum of this signal here will start to fall down at a certain rate once we reach this point, which is 1 over pi tau r, where tau r, you can see, is basically the switching time of the trapezoidal shape. So if you read this article here, you will see that the tau r is basically the transition time that we have of this trapezoidal signal. So we can actually calculate what is going to be here, this rate where the spectrum starts to fall down on a 40 dB per decade. And this means that if we add this minus 40 dB per decade, the response of the PDN that we are looking for, which is this one is growing at plus 20 dB per decade, then this means that the signal still will start to fall down at a rate of minus 20 dB per decade. So this means that really at high frequencies, we don't have to care much about how much the signal is going to be amplified. So how much the noise is going to be amplified, but this means that the harmonics which stands over this point in here, then they will start to slowly decrease at a rate of 40 dB per decade. And this means that the power that they contain is not going to be so much of a problem for us anymore. Because you can see the amplitudes then of these frequencies will become negligible. Okay, so now the question is how we're going to calculate how many capacitors do we need in our circuit to guarantee this target impedance. First of all, we have to calculate the target impedance that we are allowed to have in our system. So we need to really understand what is the target impedance that I can have for my system. And then based on this target impedance, we can then calculate how many capacitors we can have by a simple equation, which is basically twice the series inductance of the capacitor that we are choosing, divided by the target impedance times the time for the transient current required by the IC. And by that, we're going to find the number of capacitors that we need to have in order to achieve this target impedance. So when we're calculating the target impedance, we have these adjusting factor, take into account noise, temperature changes, parasitic element, and manufacturing tolerances. So that when you're doing the calculation, you can easily adjust the target impedance requirements that you have. So what is the best solution now that we can implement for our design? What is the best decoupling strategy that we can use? So first is, like we said, to calculate the target impedance. Then we choose the SMT capacitor package size. And finally, once we choose that, we can use the largest capacitance value available in this package size. And so the next point that I wanted to touch on as well is the interplane capacitance. So we know that if we use this interplane capacitance, we are going to have certain benefits for lower frequencies. So this means that we are going to use the capacitance between the planes to lower further the target impedance that we have. But this comes also at a cost, because this means that these planes, so the power and the return reference plane, they are also going to have some resonances. So these resonances in here, these resonant frequencies that they are going to have, these also will become important, because then they will show up in our impedance profile of the power delivery network. So the reason why we also want to use some capacitor with higher equivalent series resistance, so some lossy capacitors, is because we can actually use this equivalent series resistance to dampen these frequencies in here. So to dampen the resonances created by the interplane capacitance that we use. So these capacitors, they are not going to be used in here to provide the signal integrity function of providing the energy to the IC, but they're going to be used all over around the board. So all over the board, first of all, to reach the target impedance, but also to dampen these frequencies that we just show you here. So really, it will be a combination of low ESR capacitors placed all over around and as close as possible to the IC, and a little bit higher ESR spread around the board to reach the target impedance, but also to dampen the resonant frequencies of the power and return reference plane.